Alright, today we're going to talk about the periodic table of elements. We're going to get a little intro into the structure of it, and then also a little bit about the trends that we see in the periodic table. So, in the basic structure of the periodic table of elements, I would suggest that if you have not heard this lecture before, you print out this. You can find it on my Blackboard site, and you will see across the top, all those numbers across the top denote the groups of the periodic table. So every single one of these columns that you see, 1 through 18, those 1 through 18 numbers across the top, every one of those columns, so for instance, group 1 is hydrogen, lithium, sodium, potassium, all along that left side. All those 7 elements are in group number 1. So those are the groups. The columns are called groups. The periods are the rows across. And so hydrogen and helium make up period 1, whereas lithium, beryllium, boron, carbon, nitrogen, oxygen, fluorine, and neon, they make up period 2, and so on and so forth. So that's the first basic structure of the periodic table. There are 3 large groups that elements are divided into. Metals, nonmetals, and metalloids. Metals can be found right here. You can see everything from lithium down, and you can see all across. Everything in blue right here is a metal. Then there are nonmetals. Nonmetals are found here. Okay, and I've heard some confusion about this where they say, wait, but what about nitrogen? You can make liquid nitrogen or solid nitrogen. Does that make it a metal? No, solid, liquid, gas. Doesn't matter. That's not the difference between a metal and a non-metal. We'll learn about the differences between metals and non-metals later. But right now, I just need you to know that this area of the periodic table is where non-metals are found. And then there are ones that are sort of in the middle, and not coincidentally, they are also found in the middle. Between the metals and the non-metals are the metalloids, the ones that are in the middle between metals and nonmetals. They have some metallic properties, they have some non-metallic properties. And so they are found right there in the green. So here is overall the 3 main groups of the periodic table. Now they are divided further into smaller groups, so let's see what those are. Alkali metals. Alkali metals can be found right here, okay, in group 1, not including hydrogen. Alkaline earth metals are all of the elements found in group 2. Those are the ones right here shaded in yellow. Transition metals can be found right here, right in the middle of the periodic table. Basically, what we know as the d block elements. Those are the transition metals. So you know the d orbitals, and all of these elements have electrons in their d orbital, and that is where their electrons finish settling into. Those are called transition metals. There are halogens found right here in group 17. And the last group that we need to know about is the noble gases. And those are found right here. There's a reason why the noble gases are called noble. They actually don't react with anything. And so when they were discovered, scientists called them noble because they don't interact with the other elements in the periodic table. So it was considered that they didn't interact with the common folk of the rest of the periodic table, which made them sort of noble and hoity and a bit snobbish. And so they were called noble gases. So here is the basic structure of the periodic table. Right here, what I need you to know, you just need to know metals versus nonmetals versus metalloids, and whether elements fall into alkali metals, alkaline earth metals, transition metals, halogens, or noble gases. All right, now why do we organize things? You can see that these Coke cans right here are organized in a particular manner, and they are organized from darkest to lightest, and they fade as they go down. These bird bones right here, they are organized from smallest to largest. Okay. Here are some leaves that are organized by color. So you can see them going from a dark red, and then they do the whole Roy G. Biv thing, red, orange, yellow, green, blue, indigo, violet, all the way down through the colors. Now, why do we organize these things? Well, it's not just to make them look pretty or look nice. It's to be able to see a trend, be able to see a pattern. Also, if I wanted you to find a particular leaf, particular color of leaf, it would be much easier to find it in this than it would be in just a bunch of scattered leaves. If I asked you to find a t-shirt of a particular color, it would be much easier in this situation than it would be in this situation, because you see the trend, and you would be able to, based on the other t-shirts and where those locations are, you would be able to find the t-shirt location that you were looking for, whereas in this situation, it's much harder. It's much easier to find the wrench that you're looking for in this situation than in this situation. So when you organize things, you were able to see trends and find what you were looking for easily, like we did with the t-shirts or like we did with the wrenches. You can guess the location of one thing by the location of another. So if you see one thing and you say, okay, well, this has certain properties, you can say, okay, well, this thing next to it would have these properties because this is how the trend works. Okay? You can also guess the properties of one thing by what surrounds it, which is what I talked about just a second ago. So in this situation, if I were to ask you, tell me what the next figure in this series is going to be, what would you say? Just imagine it right now. Imagine in your head what's going to come next. Is it going to be this? No, that would be crazy. That would be completely out of character with the trend and pattern that we have shown here. It would be this. This would be the next thing in the pattern. And that works. And we know that because this is the trend that we're seeing. That's why we organize things. Right here, what would be the object that's going to go in this spot? Is it going to be much larger than the bullets surrounding it? Is it going to be much smaller than the bullets surrounding it? No, of course not. It's going to be around the same size. It's going to be slightly larger than the one to the left of it and slightly smaller than the one to the right of it, which is exactly what it is. So this is why the periodic table is organized the way that it is. It shows us trends. It allows us to be able to predict things about the periodic table and about the elements on the periodic table. So we've seen this picture before. We saw this picture when we talked about radiation. Well, let's talk about it a little bit more. I'm going to take these other things away for just a second. We're just going to look at the repulsive and attractive forces of the nucleus. Now, in the nucleus, we have repulsive and attractive forces. We have the repulsive force of all those positive particles. Look at all those little red particles in there. All those positive particles want to get away from each other. They hate each other more than anything on the planet, in the universe. They hate each other. They just want to get away from each other. But they stay in the nucleus. They do. They don't fly away. And so how does that happen? How can you have this force pushing outward and then still have the protons stay in the middle? Well, there must be another force counteracting that repulsive force that holds the protons in the nucleus. And that force is called the strong force, also called the nuclear strong force. And so you can see these gray arrows pointing towards the center. Those are representing the nuclear strong force. And that strong force holds the protons in the nucleus with the, once you get the right combination of protons and neutrons in there, you get the strong force which holds the protons in the center of the nucleus. The electrons have the same idea going on. You have a repulsive force. The electrons hate each other. They are negatively charged, like charges repel. And so you have this repulsive force of the electrons on each other. But you also have an attractive force of the protons on the electrons. Protons are positive, electrons are negative, opposites attract, and so the protons in the nucleus hold on to those electrons around the nucleus, and so the repulsive force and the attractive force counteract each other, and you get electrons held around the nucleus. Now, when you think about that, when you think that there is a repulsive force from the electrons and an attractive force from the protons, atomic radius makes very, very easy sense. Atomic radius is the size of the electron cloud. So if you look right here, you can see this cloud around the nucleus, and electrons are sitting in their orbitals. The size of that cloud is the atomic radius. The atomic radius decreases as you move up and to the right on the periodic table. So look at this. You can see right here, we have a large atomic radius. And as you move up and to the right, the atomic radius gets smaller and smaller. Well, we're gonna divide this trend into two separate segments. First, we're going to look at why does atomic radius decrease as you move to the right on the periodic table. Well, as you add more protons to the nucleus, so think about this, as you add more protons to the nucleus, you have a greater attractive force on the electrons. The only thing holding those electrons around the nucleus are the attractive force of the protons. Add more protons, greater attractive force, therefore it pulls the electrons closer to the nucleus and decreases the atomic radius. So that explains why atomic radius decreases as you move to the right on the periodic table. Well, why does atomic radius increase as you move down? As you move down, you are adding more protons. Look right here. As you go from hydrogen to lithium, you are adding more protons. You are also adding more electrons. And when you add more protons, shouldn't you expect the atomic radius to get smaller? Well, not exactly. In this case, when you move to the next period, you have to move up to the next quantum level. So you add electrons to the first quantum level, hydrogen, then helium. And then when you get to lithium, you have to add electrons to the next quantum level, which is much larger, which is much further away from the nucleus than the first quantum level is. And so, therefore, you increase the atomic radius dramatically. So you can see, as you move to the right, you decrease atomic radius. As you move down, you increase atomic radius. As you move to the right, you decrease atomic radius because you are adding more protons, thus increasing the attractive force on the electrons towards the nucleus. As you move down, you get a larger atomic radius because the electrons must move into the next quantum level. Okay. You can see the atomic radius trend, radii trend here. You can see when you go from hydrogen to helium, you decrease the atomic radius. But as you go from helium to lithium, you have to add another electron and it goes into the next quantum level, which then increases the radius dramatically. But then you add protons, add protons, add protons, add protons, decreasing the atomic radius every step of the way until you get to neon. And then the next electron that you have to add, you must add to the next quantum level, which is in sodium. And in sodium, you have to add an electron to the next quantum level, which makes the atomic radius much larger. Then you add protons, add protons, add protons. It sucks the electrons closer and closer to the nucleus, more attractive force, until you get to argon. And then once you're at argon, the third quantum level is completely full. And so, once you add the next electron, it must go into the fourth quantum level in potassium. And then the cycle starts all over again, where you add more protons, it decreases the atomic radius until you get to krypton, and then again the same cycle wraps around again. So that is the trend of atomic radius. Now, let's take a little sidetrack and talk about ions. We've learned about ions before. Let's talk about them a little more. Atoms like to have a full outermost quantum level. So whatever their outermost quantum level is, they want it completely full. Okay. It can be the first quantum level, second quantum level, whatever the outermost one is, they want that one full. To do this, they will gain or lose electrons and become ions. So, for example, fluorine. Fluorine has two choices to gain a full outer quantum level. Its outer quantum level is the second quantum level. So it has two choices. It can either add one more electron and get an electron configuration like neon has, or it can lose 7 electrons and then have an electron configuration like helium has. In both of those situations, fluorine gets a full outer quantum level, either by gaining 1 electron in its second quantum level, or by losing 7 electrons in its second quantum level, which then makes its outer quantum level the first quantum level, like helium has. So, what do you think is easier, to gain 1 or to lose 7? Gaining 1, of course. And so if it gains 1 electron, now it has 1 more electron than it does protons. So and fluorine has 9 protons. So if you have 9 positive charges and 10 negative charges, what charge is fluorine in that instance? That's right, it's -1 because you have one more negative charge than you do positive charge. So by adding that extra electron, you actually get one negative. Fluorine, one negative. Let's guess another one. Nitrogen. Nitrogen, you can either gain 3 electrons, 1, 2, 3, or you can lose 1, 2, 3, 4, 5 electrons. What do you think's easier? Gaining 3 electrons or losing 5 electrons? Of course, gaining 3 electrons. And so you would have nitrogen 3 minus. Its most common ion is nitrogen 3 minus. How about sodium? You can either gain 7 electrons or lose 1. Losing 1 is way easier. And so it's going to be sodium 1 plus because it would lose 1 electron, which means it has 11 positive charges, 10 negative charges, which gives it a 1 plus charge. Calcium, it is going to lose 2 electrons to get an electron configuration like argon, which will give it a 2 plus charge. Calcium 2 plus. Aluminum. Aluminum can either gain 5 electrons or lose 3 electrons. It's going to lose 3, much easier, so it's going to be aluminum 3 plus. Argon. Argon's happy. Argon's happy. Argon has a full outer quantum level, and so it's going to stay exactly the way it is. It is going to have a 0 charge. Hydrogen. This one's a little tough. Hydrogen, you might say, wait, I can gain 1 electron and become like helium, or I can lose 1 electron and just have no outer quantum level, and just have no electrons at all. And actually, it's easier for hydrogen to lose 1 electron, and so hydrogen actually becomes hydrogen 1 plus. And then finally, carbon. Carbon can either gain 4 or lose 4, and it can do either. It is carbon, it can be +4 or -4. Both situations happen equally often. So, you can see right here, a chart of ionic charges based on the periodic table. You can see that on the left-hand side of the periodic table, we have 1 plus charges, and then as you move over, you'll find 2 plus charges, then 3 plus, then plus or -4, and then -3, -2, -1, and 0. In the middle, you find this area of variable charges. We will talk about that later, but right now, I just want you to focus on the left-hand side and the right-hand side, basically the S block and the P block of elements. All right, now, ionic radius. To make an ion, an element must lose or gain electrons. Now, remember we was talking about that whole attractive repulsive thing that we talked about before. Remember this? Attractive forces, repulsive forces. Well, what do you think will happen to the radius of an element if an electron is added but no new protons are added? So what do you think will happen to the radius of an element if an electron is added but no new protons are added? Well, that means you're adding electrons and not adding any more protons. So you are adding repulsive forces and not changing the attractive forces at all. So what happens to the atomic radius? It gets larger. That's right, the electrons are pushed further out from the nucleus. What do you think will happen to the radius of an element if an electron is taken away and no protons are lost? Well, you're going to take away an electron, you're going to have the same number of protons, and so you decrease the repulsive force, attractive force stays the same, you decrease the atomic radius. So, ionic radius, definition, the size of the electron cloud of an element after gaining or losing electrons. Well, ionic radius trends in the periodic table are, if you lose electrons, you get smaller. If you gain electrons, you get bigger. Simple as that. Okay, losing electrons, you are losing repulsive forces and keeping the protons the same, which means that the atomic radius gets smaller. So in elements that lose electrons, their ionic radius is smaller than their atomic radius. And in elements that gain electrons, so elements that become negative in their ions, they are adding repulsive forces, and so their ionic radius is larger than their atomic radius. Okay. So in this chart right here, you can sort of see this. Look at fluorine in the upper right-hand corner. All right, so let's look at this. You can see that the inner gray ball, the inner gray sphere right there, that is the atomic radius, okay? But fluorine wants to add an electron. And so when you add an electron, you've added a repulsive force, and so the ionic radius is larger. That's the blue sphere on the outside. If we move over to lithium, lithium usually has an atomic radius of the gray sphere on the outside. But if you take away an electron, which is what lithium is prone to do, you get an ionic radius of the red sphere on the inside. So it shrinks because you've removed a repulsive force. And so the electrons get pulled closer to the nucleus. All right, here's a little analogy. Now, nothing to do with ionic radius. We're going to move away from that. We're going to move to something called ionization energy. So watch this. You got a little guy. If he jumps, it's going to go up. It's going to go down. Why? Because of gravity. Gravity pulls him back down to the earth. If he jumps with greater force, he can jump up really high, and then he's going to fall back down. But we all know that there is a force that this guy could jump off of the earth with that would send this person out of the gravitational pull of the earth. Okay, so if he jumped with enough force, he would just fly completely off the earth. Now, you can make an atom into an ion with the same idea. We have seen that when you add energy to an atom, we can make an electron jump into a higher energy level. So, if we add energy into an atom, we can make the electron jump to a higher energy level, and then when it falls back down, it releases the energy that it absorbed. Okay. If we add more energy, we can make that electron jump to a higher energy level, and then when it falls back down, it will release a greater pocket of energy. Now the thing is, in the same way that if the person jumps with enough force to jump outside of the gravitational pull of the earth, you can add enough energy. If you add enough energy, you can make an electron completely fly off the atom and make that atom into an ion. So, if I were to add a huge amount of energy, I could make that electron completely fly off the atom, turning it into an ion. This is the ionization energy, the energy required to remove an electron from a gaseous atom. Now, there are different types of ionization energy. There is the first ionization energy. That is the energy required to remove one electron. So if I have an atom and I want to remove an electron from it, just one, I would have to add an amount of energy equal to the first ionization energy in order to get that electron to fly off of that atom. If I wanted two electrons to fly off, I would need to add energy equal to the second ionization energy, because that would be the energy required to remove a second electron. And so on and so forth. Third ionization energy would be the energy required to remove a third electron, and you get the idea. Okay, now remember, with ions, atoms like to have a full outermost quantum level, and to do this they will gain or lose electrons and become ions. Well, which elements do you think will have the lower ionization energy, meaning it is easier to remove an electron? Okay, that's what we're going to talk about in just a second. But before we get there, let's talk about which elements want to lose electrons and which ones don't. Well, which elements want to lose electrons? That's right, it's the ones on the left side of the periodic table, because those ones are going to become positive. Those ones want to have a full outermost quantum level, and so they're going to lose electrons in order to do so. Whereas the ones on the right side of the periodic table, they want to gain electrons in order to achieve a full outermost quantum level. So, with that said, in which element in this period would it be most difficult to remove an electron? And that's right, the ones on the right. Neon, fluorine, oxygen. In those elements, it's going to be hard to remove an electron. So if ionization energy is the amount of energy it takes to remove an electron, what would be the trend from left to right of increasing ionization energy in the periodic table? That's right, ionization energy would increase from left to right. It makes sense if you know how protons and electrons work. If you know certain particular rules about how atoms and elements work, knowing the trends is easy. You can figure them out on your own. So, you increase ionization energy from left to right. What about up and down? What do you think is going to happen? What do you think the trend is going to be? Do you think ionization energy will increase as you move up in the periodic table? Or do you think it will increase as you move down in the periodic table? And why? That's the important part. Really, why? And what I want you to think about while you do this, I want you to pause it in just a second, and I want you to think about why, what the trend is and what the reason is. I want you to think about this. The closer an element holds its electrons to its nucleus, the harder it is to remove those electrons. So, okay, well, here's your answer. The answer is that ionization energy increases as you move up in the periodic table, because as you move up in the periodic table, electrons are held closer to the nucleus. They're held in lower quantum levels, which means the electrons are held closer to the nucleus, which makes it so that it is harder to remove those electrons. So again, here's the trend of atomic radius in the periodic table, and you can see that if you looked at hydrogen and looked at lithium, lithium is not holding its electrons as close to the nucleus as hydrogen is, and so it's easier to remove the electrons from lithium than it is from hydrogen, which means that hydrogen has a higher ionization energy than lithium. So ionization energy periodic trends go like this. They increase from left to right, and they increase from bottom to top. Electronegativity is the last trend that we will be talking about. It measures the relative ability of an element to attract electrons in a chemical bond, which means how much does an element like electrons? How much does it want to pull electrons close to it? Okay? What do you think the trend will be for electronegativity from left to right? If we want to look at electronegativity from left to right, well, what do you think is going to like electrons more? Lithium or fluorine? Well, fluorine wants one more electron. Lithium doesn't even want an electron. It wants to get rid of an electron. And so the trend is that electronegativity increases from left to right because fluorine likes electrons more than lithium does. And that trend is continuous from lithium all the way over to fluorine. You may ask, what about neon? What does neon do in this whole electronegativity thing? Well, if you look at the definition of electronegativity, it says, measures the relative ability of an element to attract electrons in a chemical bond. And as we learned earlier, neon is a noble gas. It doesn't make chemical bonds, and so it does not have a measurement of electronegativity. So, how about from top to bottom? Well, as we said earlier, the closer an element holds its electrons to the nucleus, the more it likes those electrons. And so, from top to bottom, you will find a trend of as you move up in the periodic table, electronegativity increases. Okay? So, an easy way to remember this is that fluorine is the most electronegative element, whereas francium is the least electronegative element. And that moves perfectly with the periodic trends of electronegativity. Here are all of the trends that we see in the periodic table. So I do not want you to remember them like this. I show you these arrows, but I don't want you to remember them like this. I want you to remember the whys. Why does atomic radius increase as you move down the periodic table? And why does atomic radius increase as you move to the left on the periodic table? Why does electron affinity, which is the same thing as electronegativity, by the way, why does electronegativity increase as you move from left to right and from bottom to top? And the same with ionization energy. Why is that happening? Remember that. Don't remember these arrows. Remember why. All right, that's all. I hope that this helped. If you have any questions for me, of course, I am always available for you to ask them. Thanks.